Okay, I wanted to talk a little bit more about the difference between conservative and non-conservative forces. Um, so we've looked at the force due to a spring. We've applied forces by just pushing on stuff with our hand, or we've had forces due to gravity. We've seen the force of friction. Some of these are conservative and some of them are not. Literally, what the term conservative in this case means is that if you calculate the work done or the energy to apply one of these forces, then no energy is actually lost. In other words, energy is conserved. And for a non-conservative force, we would say the opposite, that energy is lost. And it's not lost. It has actually turned into something else. We'll call it internal energy. So we've spoken about this already, and a good example of that non-conservative force would be our frictional force. So as we have a mass sliding across a rough surface, we're actually dislocating little pieces and sliding them over. We're creating sound, light, and heat, and that all ends up being internal energy. So if we had mechanical energy, let's say if we had it was moving with some speed, that means it has some kinetic energy equal to 1/2 mv squared. We're going to be, as it moves some distance delta x, we're going to be doing a work from the frictional force equal to mu times the normal force times whatever distance it slides through. But this is a non-conservative force, and what's going to happen is that energy is going to be transferred into something that is not mechanical energy anymore. Meaning, one, it's turning into internal energy, but it's neither gravitational, spring. We can't turn it back into potential energy in a spring. We cannot turn it back into a force of any other kind. We cannot use the energy created by friction, which is now heat, to lift a mass up some distance delta y, right? The energy is basically lost in terms of mechanical energy, but it's really turned into something else. It's turned into heat, it's turned into sound, it's turned into light. All of those things represented by basically vibrations in the atoms. So these other, the spring force, an applied force, force due to gravity, those are conservative. The applied force, some component of it could be, the whole thing does not have to be conservative. For instance, if I applied a force downwards on a mass and slid it to the right, the amount of force that we're applying downwards doesn't contribute to the work done at all, right? So that whole magnitude of the force is not necessarily conserved. Okay, let's get to some definitions for what a conservative force is then. So number one is that the work done by the conservative force is completely independent of the path taken. And I'll do an example of that. We've actually done a video, or I did a video where we did an example. If we had some weight or some force due to gravity equal to mg, and it was maybe acting in the negative j direction. If I wanted to know how much work was done, then we took the dot product of the force with the displacement, or delta R. And remember, we could move in any path we wanted. But if it's a conservative force, it's independent of the path. So all that matters is this distance h that we traveled from point 1 to point 2. Doesn't matter that we went left or right at all. So when we do the work done, we get the force of gravity as minus mg in the j direction. And remember, we could be dotting it into a delta x with I component and a delta y with a j component. And the I component doesn't matter. When we take the dot product, it goes away. Only the like components matter, the j and the j. And we end up getting the work equal to minus mg delta y to lift something up. If gravity was doing work making the block go down, the work would be positive. And that's the work by the force of gravity. Okay, definition number 2 for a conservative force. If you move in some closed path, then the work is 0. What do I mean by a closed path? Alright, let's use the gravitational example, and we can use a spring example also too. A closed path. That means we can look at this a couple ways. Say we lift some mass from the ground at point 1. We lift it up to point 2, and we bring it back down to point 3. And then we bring it back down to point 4, all the way back down on the ground. If you calculated the work to get from 1 to 2, which is all the way up, and then the work from 2 to 3, and then the work from 3 to 4, you'll find that all of those added up equals 0. So the work total would be all of them added up. And it's going to equal 0. You can also do this if you took a particle with some mass. That means it has some weight down, mg. And if you took this on a closed path, let's say you went up 3 meters. And then your next step was you went over 4 meters. And then you came down another 3 meters. And then you came back to the left 4 meters. That is a closed path. We ended where we started. If that is the case and the force is conservative, then the work is 0. So we did, gravity did negative work, or we had to do positive work lifting the block up. We did no work moving it over to the right. We gained that, how can I say it? Gravity did positive work bringing it back down here. And we did no work over here. So the only work done was the mg delta y for the positive 3 meters and the negative 3 meters. And then those both canceled out. We get a total work equal to 0. So if you end up where you start, that's called the closed path. And the work along a closed path is equal to 0. And that works only for conservative forces. Okay, so if we look at internal forces, the work done on a how can I say this? We can associate the potential energy for a system with the force acting between the members of a system. We're just looking at one object right now, but we can only do this if it's conservative. In general, we can say that the work done by a conservative force on an object changes from one configured, as the system changes from one configuration to another, is equal to the initial value of the potential energy minus the final value. So we'll say that the work done, kind of like our other definition from work, is equal to our potential energy in its initial state minus the potential energy in its final state. So that's going to be a minus delta U. This has to do with work and potential energy, right? We also had a definition that work is equal to the change in kinetic energy. So that's work and turning into the change in 1/2 mv squared, right? So you'd have 1/2 mv final squared minus 1/2 mv initial squared. So two different things used for different scenarios, but basically the work done is equal to the change in potential energy. If I had to lift a mass up and do so much work, right? Force times delta y, and that's the force is mass times gravity, and I lifted it some delta y. Well, that's exactly equal to the potential energy up here of this mass, mgh. Same exact thing. So that's all this is saying, except for the work done by gravity, if you remember, would have been negative. So we have this minus sign in here. Okay, so the same thing goes for a spring too. If we took a spring, maybe put a mass on here, something like that, and we let this thing oscillate. If we call this our equilibrium position, x is equal to 0, and we pulled it out some delta x, that required work. It required us doing work to pull the spring out and stretch it. Now if we let it go back exactly the same amount to its equilibrium position, that amount of work would cancel out. Exactly, that is a closed path. You could let this thing oscillate back and forth 50 times as long as it just keeps going back between the same 2 points, and as long as it finishes in the same place it starts, that's a closed path. And when a spring oscillates, we do lose some energy to heat, but we're going to ignore that for now. Now, non-conservative forces are a little bit different. They do depend on the path taken. So let's take a look at those. So for instance, let's say our path looks like this, and this is a profile view, maybe like a roller coaster, but I got a book sitting here. This book has some weight, mg, and there's some rough surface, so we're going to have some frictional force pointed backwards the whole time. Now, if I push this along this path, it's going to have a delta S equal to the length of that path. If I drew a line from where we started at 1 over to where we finish at 2, this line right here, right, by definition, the distance between 2 points is a line, and that's the shortest distance between 2 points. It is shorter than delta S, so the length of the line is less than delta S. So therefore, we would have to push against a less friction, right? We would lose less energy to friction. This shows the difference between conservative and non-conservative quite well. The path changed. One path was much longer. When we reduced the path length, the amount of work we had to do due to friction is less. So the work of friction would be mu k times the normal force and times that delta S. If delta S is very large, the work's going to be large. If delta S is smaller, the work will be smaller. Okay, next I'll show you how to determine relationships between conservative forces and a potential function or potential energy.